Let's look at 3.2 part 2. So we were talking about standard deviation and variation and variance. So we are going to learn how to interpret standard deviation. Standard deviation measures the variation among values. So values close together, our standard deviation will be small. And that means little variation. If the values are further apart, your standard deviation will be large. So further apart means that your values are varying. So we have a lot of variation. With this data, the standard deviation, we didn't actually find it, but whenever you put the data in, I'm just going to show you. So I went ahead and on the left side, I have my the Old Faithful. And then the right side, well, L2, I went ahead and put in the lead in the air. Remember, we had this 5.4, which was an outlier. It's like completely higher than all the rest of them. So what you can do, if you have two different sets, if you want to put one in L1, one in L2, whenever you go in here for calculate, and you're doing one vary stats, I can actually change my list from L1 to L2 by using second, and then look at these buttons down here. See how it has in blue L1, L2? Those are all your list. So that makes it where if you're using these same data sets like we have been for all these notes, the Old Faithful and the lead, you can interchange between them without deleting a whole set. So I'm just looking at L2, which is the lead in the air, and I'm going to calculate. And I know that the mean is 1.538. And SX is your standard deviation for the sample, and that was 1.914. And the reason why I'm doing so many numbers past the decimal is because you do one more than your data set. So we went 3 decimal places. So this standard deviation, even though it's just 1.91, we'll compare that to what the mean is. The mean is 1.5, but the standard deviation is 1.9. So it varies quite a bit, even though that variation just seems kind of small. Well, in relation to your data. So you have to look at what your data is, what your mean is. Okay, we have another way to interpret the standard deviation. We can use the range rule of thumb. The way we use this is we're going to do an estimate where you can do our range divided by 4. So to interpret a known value of standard deviation, we're going to look at minimum usual values. So these are not your outliers, and then maximum usual values. This will help determine if a number is unusual. So any number that's unusual is outside of these 2 usual values. So you will do this by doing your mean minus 2 times your standard deviation. That's your minimum. So you take your mean and subtract 2 standard deviations from it. And then for your maximum usual value, you'll take your mean and add 2 standard deviations to it. So if we think about this like a number line, in the middle is our mean, x bar. So if I take X bar and I add 2 standard deviations to it, it's going to come out here. X bar plus 2s. And then if I go back to the mean, I go below it. It'll be X bar minus 2s. So everything between here is considered usual values. But beyond that, those are considered unusual. Not very likely to get. And what this actually is, you're going to learn from that empirical rule, is that 95% of your data, if this is a normal distribution, lies between 2 standard deviations above and 2 standard deviations below. 95% of your data will fall in that, in between those two numbers. Okay, we can also use this, I forgot what it's called, just an estimate, range divided by 4. So let's look at the Old Faithful example. We would need to find the range of Old Faithful and then divide by 4. So if we look back, range is found by doing max minus min. So look at our data. What's our maximum value? 98. And our minimum, 65. So we're going to subtract those and divide by 4 to find this estimate. So and what does that come out to? 0.5. 8.5. I got 8.25.
Or no, I did my mistake. I did 64.
Oh, okay. Yeah, that'll.
I pressed it.
Okay. Yeah, so 8.25 is the estimate for standard deviation without knowing any other values. All the values that we needed for this kind of estimate is your max and your min. So let's compare that to what we actually got. It's 8.9. That's pretty close. 8.9 compared to 8.25. It's pretty close to original, the actual. Okay, so let's find some usual and unusual values. Remember how we said 65 seems like an outlier? We can actually back that up with some data, some information. So it says estimate the minimum and maximum usual values for the Old Faithful data. So we would need to first know X bar, our mean. So look back at through your notes for X bar and our standard deviation.
It's 91.25.
Yeah. So that's our mean. And then our standard deviation, what was that? Yeah. So let's find our max usual value. So we're going to take X bar and we're going to add 2 standard deviations to it. So 91.25 plus 2 times 8.9. If you want to write that down before we actually plug it in. Because standard deviation is how far away are you from the mean. So this is saying most of the values are 2 standard deviations away from the mean. So that comes out to 109.05. So let's do our minimum usual. So we're going to do mean minus 2 standard deviations. That comes out to 73.45. So we can put this on a number line because all the data values would fall on a number line with our mean in the middle. So I'm going to put X bar, which is 91.25. 2 standard deviations above 109.05. And then our minimum usual value, 73.45. So X bar minus 2 standard deviations. So anything between here are usual. Anything outside, everything over here is unusual. Same thing over here, unusual. So basically it's an outlier. If it's outside, that's terrible handwriting right there. Okay, so our value of 65, that minimum value, that falls outside of our usual values. So 65 is below the minimum usual. Okay, let's look at example 2. Use the samples describing the amount of lead in the air to find the minimum and maximum usual values. So X bar and our standard deviation. We just wrote that on the last page. X bar. Yeah. And standard deviation. 1 point, what? 4. So let's find our max and our min usual and determine whether 5.4 is considered unusual or not. And then our min usual. Negative 2.29. So having a negative lead value, that doesn't make sense, right? So truly it would be 0. So whenever you look at it on a number line, 1.538 is your mean. And then you would go up to 5.366 and down to negative 2.29. So everything between there would be usual. So is 5.4 considered unusual? Yeah. So it's considered unusual because it is below the minimum unusual. Minimum usual. We're going to skip mean absolute deviation. That's the next part. That was something y'all learned in 8th grade, and it's not helpful. We don't use it in statistics, so we're skipping that. And we're going to go to the empirical rule. So if your data is a bell-shaped distribution, so normal distributions, and you will be told this is a normal distribution, then asked a question. So if you know that's a normal distribution, you can determine how much of the data is in each part. So this is just a bigger one. It's right here, but it's so small. So I put it right here. I made it big and uploaded it and let y'all have a copy. So let's look at this empirical rule. So your mean is in the middle because this is a normal distribution. Remember, with normal distributions, we have mean, median, and mode are all in that center. So if you go below by 1 standard deviation and above by 1 standard deviation, 68% of the data is within those boundaries. 1 standard deviation away from the mean. If you make your boundary a little bit bigger and you go 2 standard deviations above and below the mean, then this is where you get that 95%. If you go 1 more standard deviation, it's almost all of the data. Look at how much it is. 99.7% of the data are within 3 standard deviations. So we use mean and standard deviation to find out where most of the data is. So this is a really good chart to refer back to about mean and standard deviation of normal distributions. So I put on here normal distributions. We use something else for things that are distributions that are not normal. Okay, so chevs theorem, kind of a weird name. The proportion or fraction of any set of data lying within k standard deviations of the mean is 1 minus 1 over k squared, where k is any positive number greater than 1. For k equals 2, k equals 3. So a little bit confusing, but what this is for non-standard deviation. So right down here it tells you. Empirical rule applies to only the data sets with bell-shaped distributions. Chevs theorem applies to any data set. So that's why we need to learn it. So what we're going to do is, if we plug in k equals 2. So k equals 2. K is how many standard deviations away from the mean the data is. So the way you find it is by using this formula. So 1 minus 1 over k squared. So when k is 2, so we're looking at 2 standard deviations, 1 minus 1 over 2 squared. So I'm going to reduce it and solve it. 1 minus 1/4. If I have 1, I take 1/4 away. What do I have left? 3/4. So that comes out to 75%. So this is saying with any data set, 75% of the data is within 2 standard deviations of the mean. So I'm going to put that here. At least 75% of the data is within 2 SDs of the mean. That's chevs theorem. So we got that from using this formula that's part of the theorem. So when k is 3, we're going to use that same formula, k is 3, and do 1 minus 1 over 3 squared. So that's 1/9. If I take a whole, take 1/9 away, how many ninths do I have left? 8 ninths. Let's put it as a percent. 88 or 89 if we round, because it's like 0.888. Yeah. Okay. So at least, oh, this should go up here. Sorry, that's another example. So at least 89% of the data is within 3 standard deviations of the mean. Knowing that it's a normal distribution, though, gives us a better number, right? Because within 2 standard deviations on normal distribution, that's 95%. So knowing that it's a normal distribution is telling us it's 95%. It lowers it down if it's not normal, not a normal distribution. There's an example of IQ scores. That'll be the example we look at. Do you know what the mean IQ score is? It's 100. With a standard deviation of 50. 15, sorry. I said 50. 15. If we don't know if it's normal or not, then what is 2 standard deviations of the mean? 2 standard deviations would be 130. 130 to 70. So IQ score of 130 to 70 is 75% of the data. So 75% of the data will fall between 130 and 70. But later we're going to find out that IQ scores is actually a normal distribution. Okay, the last concept in 3.2 is coefficient of variation. So for a set of non-negative sample or population data, the coefficient of variation, it describes the standard deviation, so SD, relative to the mean. And it's going to be expressed as a percent, written as a percent. So what we're going to do is we're going to take our standard deviation and divide by our mean to get our coefficient of variation. And this is going to help us be able to compare 2 data sets that are completely different. So the higher the coefficient variation, the more variation among the data values. you want there to be little variation in your data. Because if you have little variation in your data, you'll be able to use that data to make predictions. But if there's a large variation, it makes it hard to use it to make predictions. So let's look at the coefficient of variation for the Old Faithful. You just take your standard deviation and divide by your mean. And then change it to a percent. So we have 8.9 divided by 91.25. We're going to go 3 places behind the decimal. Or maybe it's 2. So then we're going to move it because it's going to be moved into a percent. So that actually comes out to 9.8%. So the coefficient of variation is 9.8%. So that seems low, right? It's not close to 100, so that's good. So let's see if we can find the coefficient of variation for the lead data. 1.9114 over the mean, 1.538. So when we move the decimal, we get 124.4%. So the coefficient of variation is 124%. It's large. So which data set varies more? It'd be the second. Because the constant of variation, coefficient of variation, is much higher. Okay, biased and unbiased estimators. The unbiased estimator is your sample variance because it targets your population variance. If you find your sample variance, it should be very, very close to your population. Standard deviation is biased. It does not tend to target your population standard deviation. Okay, so there was one problem I wanted to show you on your assignment, so let me pull that up.